Hello everyone and welcome to the Minisymposium Fluids in Nanoporous Media at the Interpore 2020. My name is Gennady and I'm the chair of this Minisymposium and also I'm the presenter here, and it's my pleasure to talk today about the density functional theory model for adsorption-induced deformation of materials with non-convex pore geometry. I know this is a long title, but I'll explain you all in details and you understand this is quite simple. So first let me start from introducing the first author of this presentation. This is Dr. Andrei Kolesnikov. He's a researcher at Institute for Non-Classical Chemistry in Leipzig, Germany, and he also spent a semester with me as a visiting research scholar. So we recently completed this work, and a few days ago it was accepted to the Journal of Physical Chemistry C, and it's available online. All right, adsorption-induced deformation. Maybe many of you are familiar with this phenomenon. It's quite ubiquitous. In fact, all porous materials, when they absorb fluids or liquids or gases, they deform, they change their shape, they change their size, they swell, they contract. And an example which I typically bring when talking about adsorption-induced deformation is a pine cone, like you see here on this picture. So when it's dry, what the pine cone opens. When it's humid, the pine cone closes. While these change in shape takes place because of adsorption of water vapor in the porous structure of a pine cone. And here in this picture, in fact, what you're seeing is not a real pine cone. It's an artificial pine cone made by this group in Austria. And this artificial pine cone is made of nanoporous silica, and it behaves similar to the real one. So this phenomenon, adsorption-induced deformation, is clearly needed for fabricating devices for sensing and actuation. Another application of adsorption-induced deformation is related to the to extraction of coal bed methane and CO2 sequestration. So in this picture, this is a sketch of a piece of coal which has methane absorbed in its pores, and if we'd like to extract this methane, we can inject CO2. CO2 will be preferentially adsorbed, methane will be desorbed, we'll get methane, we'll get rid of CO2, but in this process what's happening is the stresses in the system changes, and the fractures in this coal system, they close, and the adsorption-induced deformation, in fact, significantly complicates the methane extraction process. And I have to admit that adsorption-induced deformation has been studied for many years, and a few years back, together with my co-chair of this symposium, Professor Patrick Huber, and also with Noam Bernstein, we wrote this review paper on adsorption-induced deformation. And if you're interested in the history and the development of different experimental methods and theoretical methods to study adsorption-induced deformation, I strongly encourage you to take a look at this paper, which is available open access on the Applied Physics Reviews website. So when we study adsorption theoretically, adsorption or adsorption-induced deformation, well, we typically want to model the pores as simple as we can. And typical pore models are cylindrical here on the left, spherical or slit pores. And they often work well. However, there are many materials where these models are not ideally applicable. In particular, here's the picture of hierarchical templated mesoporous carbons, which are composed of these mesoscale struts, and the pores themselves are this system of hexagonally arranged rods, and the adsorption, in fact, taking place not inside a cylinder but on a surface of a rod, and that could that could be quite differently from all the three pictures here on the left. So some years ago, together with Matthias Thomas and Alex Neymark and Katie Sikosh, I studied nitrogen adsorption in materials which are called CMK3 carbons, these materials with these hexagonally arranged rods. And in particular, we developed a DFT model for nitrogen adsorption in these CMK3 carbons, assuming the pores to be cylindrical, right? So using conventional model and applying it to these unconventional materials. And the model worked well, and in fact was even implemented in the Quantachrome instruments porosimeter. However, from looking at this picture of CMK3 carbons, it's clear that cylindrical pore is an oversimplification. So our goal right now is to develop a DFT model for gas adsorption on CMK3 carbons using a more realistic pore shape, and moreover to develop a DFT model for adsorption-induced deformation of CMK3 carbons, and that's what I'm presenting here today. So the method we're using is the classical density functional theory, and I'll give some details of the theory we used. So we used it in the local approximation, and I'll tell a few words later why. So the starting point for the DFT, for density functional theory, is an expression for the grand thermodynamic potential of the fluid, omega. And it is presented as a functional of the density profile, of the fluid density profile, rho. It's given as a sum of the intrinsic Helmholtz free energy of the fluid and the term related to the solid fluid potential of interactions, and the term related to the chemical potential mu. In order, at each value of chemical potential, we need to solve the earlier Lagrange equation for the equilibrium density profile to find the equilibrium state of the system. And of course, well, the solution of these equations very strongly depend on the form of the Helmholtz free energy and the form of the external potential phi. So Helmholtz free energy we present as the two terms, the ideal term and the excess term. The ideal term is given by the simple local expression, and the excess term is given by this repulsive free energy, which we take from the scaled particle theory, and the attractive term, which we take in the mean field approximation, where phi ff is the attraction part of the interparticle potential. And here we assume that our fluid-fluid interactions are given by the square well potential. So the key thing for the CMK3 carbons, for these templated carbon materials, is the geometry. So our solid fluid potential needs to take into account for the specific geometry for these hexagonally arranged rods depicted here on the left. So the overall potential is a sum of potentials from 7 rods, and the potential for each of the rods is given by this expression, which obtained from integration of Lennard-Jones potential assumed for solid fluid interactions. So once we set this up, well, another thing is to parameterize the model, and we took some of the parameters from the literature, while some of the in particular, some of the parameters, in particular the fluid-fluid interactions, are fit from the experimental densities of coexistent phases, surface tension, and saturation pressure at 77 Kelvin. And we use here, of course, the model for nitrogen adsorption, the gas which is most widely used for the adsorption characterization purposes. So here I summarize the parameters, and once we have all that, we can rewrite the equation for the density profile in this form and then solve it iteratively. So that was just prediction of adsorption, but that's not all what we need. We also want to model the deformation, and we will consider the system in 2D. We will consider only the deformation in plane. I'll flip back to the slide with pictures. So we assume that that the deformation takes place only in this plane of the slide. So we assume that all the rods are connected with a certain number of elastic springs. So then the elastic free energy can be written by this harmonic expression. Then we can consider the thermodynamic potential for the mu pt ensemble, this delta G, and minimization of delta G, which includes both elastic free energy and adsorption free energy, can give us the Solvation pressure, the pressure which drives the deformation, the adsorption-induced deformation, and that is given by the equation 12. And I want just to show for a comparison the Solvation pressure, the expression for the Solvation pressure for the simple cylindrical pore system, which has been frequently considered by myself and by other researchers. And when showing the results, I'll start from showing what we have for cylindrical pore. So results for the cylindrical pore. On the left, I'm showing adsorption isotherms calculated by our DFT model for cylindrical pore for nitrogen adsorption at 77 Kelvin, this leftmost curve, 90 Kelvin, the right curve, the middle curve, and the green curve is 110 Kelvin. So these adsorption isotherms are typical adsorption isotherms for the mesoporous materials. They're fully consistent with earlier works based on DFT and other methods. So on the right, we calculated the Solvation pressure corresponding to each of these adsorption isotherms, and they are also fully consistent with what was done previously. In particular, they show two regimes of adsorption-induced deformation. First, this Banham expansion, so the expansion at low pressures. Then we have capillary condensation, and after the capillary condensation we have another region of expansion, which is due to the decrease of Laplace pressure. So I'm not going in details explaining this. This has been published almost a decade ago in my paper with Alex Neymerk, and then revisited by myself and Noam Bernstein in 2016. So I want to focus on the CMK3 materials. So here on the left, we show the adsorption isotherms, same temperatures, 77 Kelvin, 90 Kelvin, and 110 Kelvin. And you can immediately see that unlike the previous case, we have two hysteresis loops on these isotherms, so two phase transitions. So the Solvation pressure in these cases, as you can see, has three characteristic regions. So 1, 2, and 3 here. So initially we have no deformation, then we have contraction, and then we have this expansion region, which is again this logarithmic trend is well known in the studies of adsorption-induced deformation. So this is again due to the decrease of the capillary pressure. So in order to understand what's going on there, it's instructive to show the density profiles corresponding to different regions. So here at the low pressures, what we have these adsorption of polymolecular films on the rods of the CMK3 carbons. So these films grow to a certain extent, and then a capillary condensation takes place. However, this is not a full capillary condensation, but this is formation of liquid bridges. So it's a phase transition up to this point, up to these points here in the middle, and this region is not relatively small, and after that, if we further increase the vapor pressure, we have another phase transition, and that is a true capillary condensation. So here the pores are entirely filled with a condensate, and well, it looks pretty much like what we would have on cylindrical model or a spherical pore model. So if we look at these profiles in the context of the obtained solvation pressure, it will also explain the behavior. So initially, when we just have these thin liquid films on the rods, they do not stretch the springs, they do not cause contraction, they do not cause expansion. So the deformation in this initial region is zero. There is no Banham effect, unlike in cylindrical pores. After that, when we get to the bridged phase, when we have this first phase transition, we drop here, and there is this significant contraction. This contraction is caused by the liquid bridges because they pull the rods together. They're trying to pull the rods closer to each other. And then after that, we have these second phase transition, and then this logarithmic curve is related to the Laplace pressures, similar to a normal cylindrical pore. So with that, I'd like to conclude. First of all, the local DFT, a relatively simple tool which is much cheaper than non-local DFT or QSDFT, and which can be used for these two-dimensional problem. So local DFT is a suitable tool for predicting adsorption and adsorption-induced deformation in complex pore geometry. In CMK3 materials, bridge formation changes both the adsorption isotherms and solvation pressure. Solvation pressure shows a trend which is qualitatively different from the cylindrical pore model, and that's extremely important. The model which we developed can be further extended to other materials with non-convex pore geometry, such as silica colloidal crystals or synthetic opals, and other materials in which pores are formed by the spaces between the spherical grains. And once again, I want to emphasize that this work has been recently published, and if you have any questions, please contact me, and I'd be happy to discuss it in more details. With that, I'd like also to thank Professor Yuri Budkov from Moscow for multiple fruitful discussions. Also, the funding agencies, the German Academic Exchange Service, which helped Andrei to come to NJIT and work on this project with me, and the National Science Foundation, which funded my research on adsorption-induced deformation. Thank you very much for your attention.